Hello, in this video we're going to introduce the idea of priority queue and binary heap. So the motivation for priority queue is because oftentimes we work with data that has some kind of priority. So let me just give an example of that. Every day we use smartphones or computers, and we often multitask on these devices. Right. So the different tasks have different priorities. So typically, the task that has the highest priority is what's called real-time tasks, such as feeding audio signals to your headphone. So if those things don't happen in real time, like there's a delay or a hiccup in sending the audio signal to your headphone, then you will hear all these weird kind of static noise, and which could make speeches or anything else very unpleasant or very unintelligible. So yeah, real-time task typically has the highest priority, and then the next task that might have higher priority as well was typically the UI interaction, such as you're typing something, right? You're responding to an email, you're typing a Word document, and that kind of thing. Now, no matter how fast we type, we probably can type just maybe 60, 70 words a second. So that data rate compared to playing music is a lot lower, but still, if the UI doesn't respond well, like there's severe lags, like in some of the early Android phones from, I don't know, 5, 7 years ago, then it makes for very unpleasant user experience as well. So, and then there are typically these, background tasks such as updating apps. They don't have to happen right at the moment. I mean, they can wait until in the middle of the night when the phone or the computer is not being used. So these are typically tasks that have the lowest priority. And so this is a very simplified view, obviously, but it gives us an idea that for multiple tasks, our devices will constantly have to pick the task with a higher priority to run them. So these tasks are typically stored in what's called a priority queue. Now, what can priority queue actually do? Well, from the previous example, we can see it really is fairly simple. It really does only two things. One is, you want to be able to insert, we want to be able to add data. And these data would have to have some sort of priority, right? And then the second thing that it needs to be able to do is that we want to be able to retrieve the data with the highest priority, and then the data with the highest priority is also deleted from the queue. So that's really it for priority queue. Now the data itself, as we see, the data itself must support some sort of ordering by the priority. Right? And so, for example, in Python, the way to implement that is probably in the form of an overloaded less than operation, that we can, say one task has a higher or lower priority than another task. So priority queue really doesn't sound that complicated, right? And as a matter of fact, some of the data structures that we studied before, we can use them as priority queues. So for example, we have ordered linked list, and ordered linked list obviously it supports insertion. So we can add data to it, and then we can look for a minimum or a maximum in the linked list, and then we can remove it. So that we can use that as a priority queue. Also, binary search trees. It again supports insertion, and we can look for minimum and maximum items, and we can remove those items. So we can also use a BST as a priority queue. However, there are problems with using these two data structures. So linked list, the biggest problem with the linked list, as we all know, is most operations are order of n. So that's linear, and it's very slow when the number of items gets large. So we want better performance. Now, binary search tree has good performance. Most operations on average are O of log of n, so that's good. However, it's not very efficient in terms of space utilization. And the main reason for that is each of the nodes in binary search tree, they have these child references, these pointers, right? And these pointers, they're not free, especially on like 64-bit machines where each pointer or each reference is 8 bytes. So each node would have 16 bytes of pointers, and that's depending on that's an overhead, and depending on the size of your data, that can be a lot of overhead or a little overhead. And also, binary search tree is very flexible. It supports all sorts of other operations. Now, we really don't need most of those other operations for priority queue. So instead of using one of the data structures that we've already studied as a priority queue is actually usually implemented as something called a binary heap. So a binary heap is just a binary tree, but it has two additional properties. The first new property is called a shape property, that it's a complete binary tree, and I'll explain what a complete binary tree in a moment. And then the second property is what's called a heap property. Your readings actually call it the heap order property. And what the heap order property is that the key stored in each of the node or the data, it must be either greater than or less than the keys in the node's children. So there's some sort of ordering in this, and obviously it could be if duplicates allow, they can be equal as well. So anyway, these are the two additional properties to a binary tree that makes a binary tree a binary heap. Now, just a bit of history, and binary heap was invented in 1964 by Williams, and it's actually a data structure that he used for heap sort, which we'll talk more about later. Now, so let me explain what a complete binary tree is. So a completely binary tree is, well, obviously a binary tree, and this binary tree, every level in this binary tree, except possibly the last level, which is the lowest level, every level is completely filled. Okay, meaning there's no missing node at that level. And then at the last level, all the nodes are as far left as possible. So remember this definition, and let's actually look at some examples. So based on the previous definition, can you look at these three trees and try to figure out if they are complete binary tree or not? So assuming you've done that, the first one is a complete binary tree because the first level has the highest level has all the nodes there, right? There's only one root node, and then the second level has two nodes, and that's all nodes. That's as many nodes as there can be on the second level. Now the last level, the third level, something node is missing, but it's okay. The last level is not required to be completely filled, and then all the nodes are as far to the left as possible, right? The missing one, the last one, is on the right side, so it's fine. So this is a complete binary tree. What about the second tree here? Well, it's not completely in binary tree because this node is missing a left child, right? So the nodes in the last level are not all the way to the left side. So this is not a complete binary tree. What about this third tree here? Well, so there is a level that is not completely filled, namely the third level here. Okay, because there could have been another child here, child node here, but it's not there. So this is not a complete binary tree either.